There are moments in cinema that are so grand, so filled with wonder, they permanently change how we dream about the future. For me, one of the greatest is in the film Interstellar. The crew of the Endurance approaches a perfect, shimmering sphere floating silently in the blackness near Saturn. It's not a planet. It's not a star. It's a distortion, a window, a doorway. As they pilot their ship into its depths, the universe dissolves around them into a breathtaking, multi-dimensional tunnel of light and shadow. They aren't just traveling fast, they are cutting a corner through the cosmos itself. In minutes, they traverse a distance that would have taken tens of thousands of years, emerging into a completely different galaxy, hundreds of millions of light years from home. This is the ultimate promise of science fiction. It's the Bifrost Bridge in Thor, instantly connecting Asgard to Earth. It's the central premise of the entire Stargate franchise, a network of cosmic shortcuts that turns the galaxy into a traversable neighborhood. The idea is so powerful because it solves the single greatest problem of space travel: distance. It tells us we don't have to spend millennia crawling through the void. It says we can take a shortcut. But is this beautiful, elegant solution real? Is this cosmic doorway, this wormhole, a genuine physical possibility that we could one day use? Or is it just Hollywood's most brilliant magic trick? To answer that, we have to go back once again to our favorite guide through the strangeness of the cosmos, Albert Einstein. When Einstein developed his theory of general relativity, he gave us the modern picture of gravity. He told us that space and time are not separate things, but are woven together into a single four-dimensional fabric, space-time. And he told us that massive objects like planets and stars don't pull on other objects, they bend and warp the very fabric of space-time around them, and other objects simply follow those curves. Now, once you have equations that describe space-time as a bendable, flexible fabric, physicists can't help but play with them. They ask, what are the most extreme possibilities? What weird shapes can space-time take? And one of the earliest and most fascinating solutions to these equations was discovered by Einstein himself and his colleague Nathan Rosen. It's called, fittingly, an Einstein-Rosen Bridge. You and I know it by its much cooler, catchier name, a wormhole. The concept is surprisingly simple to visualize, and it's one of the most famous analogies in all of science. Imagine that space-time is this simple sheet of paper. Point A is our solar system. Point B, over here, is a star in the Andromeda Galaxy, 2.5 million light-years away. To travel between them normally, we have to crawl all the way across the sheet of paper, a journey that is, for all practical purposes, impossible. But remember, space-time is flexible.
So what if we could bend it? We've folded the universe, bringing our destination right next to our starting point. The distance through 3D space is still enormous, but the distance through this higher, fourth dimension is now tiny. All we need to do is punch a hole straight through. This tunnel, this shortcut through a higher dimension, is a wormhole. It's a bridge connecting two vastly different points in space, or even two different points in time. It's not a ship traveling fast. It's a manipulation of the universe's geometry. And mathematically, according to Einstein's own theory, it's perfectly possible. We have a map to another galaxy. So we have the theory, we have the map, but can we actually make the journey? The answer, unfortunately, is where the Hollywood dream ends and the nightmare of physics begins.
So, let's imagine we find one, a naturally occurring wormhole, just like in Interstellar. We point our ship towards its shimmering mouth, and we go for it. What happens next? The very first problem, and it's the biggest deal breaker of all, is stability. A wormhole, as described by Einstein's equations, is catastrophically unstable. It's not an open door, it's a door that is slamming shut at the speed of light.
How fast is that? The moment a wormhole might form, it would expand to its maximum size and then collapse back into a singularity in such an unbelievably short amount of time. We're talking on the order of the Planck time, the smallest possible unit of time, that not even a single photon of light would have enough time to travel all the way through it.
It's like trying to run through a hallway where the entrance and exit are slamming shut towards the middle, a trillion times faster than you can even blink. Before your ship could even fully enter the mouth, the wormhole would have already collapsed, pinching off space-time and crushing your ship into oblivion.
So, why didn't this happen to the crew of the Endurance? The film actually gives a subtle hint. They say the wormhole is peaceful, that they placed it there. This implies that the wormhole isn't natural. It's an artificial construct. It's being held open.
Which brings us to problem number 2. What could possibly have the power to prop open a doorway in space-time and fight against the crushing force of its own gravity? Well, say hello to our old friend from the warp drive discussion, the universe's most sought-after and unobtainable ingredient, exotic matter.
That's right. In order to stabilize a wormhole and keep its throat from collapsing, you would need to thread it with a substance that has negative energy density, or negative mass. You would need matter that has anti-gravity.
Remember our bowling ball on the trampoline? Normal matter and energy create a dip, a gravity well that pulls things in. A wormhole throat is an extreme version of this,
wanting to collapse in on itself. To counteract that, you would need to line the inside of the tunnel with this exotic matter, which would create a powerful outward push, a sort of anti-gravity scaffolding that props the tunnel open against its own immense gravitational forces.
As we've discussed, we have no idea if this kind of stable macroscopic exotic matter can even exist. It might just be a mathematical ghost. So not only is a natural wormhole a death trap, but building an artificial one requires a material that likely violates the known laws of physics.
But let's keep dreaming. Let's say we find a chunk of exotic matter. We build our stable wormhole. We've solved the first two problems. Now, we just have to survive the trip inside. And this is where we encounter problem number 3, the cosmic noodle maker. The scientific term is extreme tidal forces, but the more descriptive nickname is spaghettification. Gravity gets weaker with distance. When you're standing on Earth, the gravitational pull on your feet is slightly stronger than the pull on your head. The difference is so tiny, you'd never notice it. But near a singularity, or inside the intensely curved space of a wormhole's throat, these tidal forces would be astronomical.
As your ship enters, the pull on the front of the ship would be trillions of times stronger than the pull on the back. The ship and everything in it would be stretched, and not just a little bit. It would be pulled apart, elongated into a long, thin stream of atoms, like spaghetti. You wouldn't just be killed, you would be fundamentally unraveled and dismantled atom by atom. This is not a peaceful journey through a tunnel of light. It is a one-way trip into a subatomic blender. So, where does that leave us? We have this beautiful mathematical concept born from the mind of Einstein himself. It offers a solution to our greatest limitation, the promise of turning the entire universe into our backyard. We have a clear, simple analogy, folding paper, that makes the idea feel intuitive and real.
And yet, when we look at the actual physics, the dream unravels. To be traversable, a wormhole must be stable. But natural wormholes are fantastically unstable. To make them stable, you need an impossible ingredient, exotic matter. And even if you could somehow acquire this ingredient and build a stable bridge, the very act of passing through it would stretch you into a stream of fundamental particles due to horrifying tidal forces. And we haven't even touched on the lethal doses of radiation that would likely be focused at the wormhole's entrance.
Every single step of the way, a wormhole seems less like a doorway and more like a beautifully constructed trap. So, is it just fantasy? For human travel, right now, it certainly seems so. The wormhole is one of the most elegant and romantic ideas in physics, but it's an idea that seems to be ruthlessly contradicted by all the other laws of the universe.
It's a beautiful concept, seemingly trapped inside the beautiful, unbreakable rules of the reality it seeks to bend. It reminds us that while our imagination can soar without limits, the universe, it plays by its own very strict set of rules. And for now, taking a shortcut isn't one of them.